We have a lovely Dubai morning, and we're excited to share with you not only the news in IDEA StatiCa version 26, but we will have also very fascinating topic of stiffness analysis. You've definitely been there. You need to assess whether the connection is rigid, semi-rigid, or pinned, what to do, right? So we will be covering that. Myself, Jan Barta, Managing Director of GSD IDEA, and today with me, I have two of my colleagues, as usual. You're familiar with them. First, ladies first. So Rose, how are you?
Hello, Jan. How are you? And hello everyone.
All good, all good. Happy to have you. And my second colleague, Venkatesh Avanidi. Hi, Venki, how are you?
Hello, Jan. I'm good. And hello, all.
Very good. So before we kick it off, as always, we're using Demio platform. Just a quick orientation. Chat in the right-hand corner to ask a question, comment, say if you like it, how you're doing, what you're interested in, tips, tricks, whatever you wish. Poll next to it. We will have quite a few of them if we are on time. If not, we might skip some. So next to the chat panel, you will be able to respond into our 4 or 5 polls we have ready for today. And for the first time, we will be also using handout section at the end, later stage of the webinar, so you can find a few resources that we'll be sharing at the end. Very good. V26 of IDEA StatiCa and what's new, specifically curated for UAE, Saudi, Qatar, GCC in general projects. Stiffness analysis, the second biggest topic. We have a small agenda. We would like to introduce new applications that our team developed for the GCC market. Fascinating topic as well. And Q&A section at the end. But as mentioned, you can ask questions throughout the session. If we're able to, we will be answering them. If not, we will answer at the end. And at the end, there is a dedicated session. So as long as you are there, you're asking questions, we are here as well, and we are responding. Before we get to the topics, just a quick reminder of how IDEA StatiCa helps engineers in the GCC in 2026. Complex connections. Everybody knows IDEA StatiCa for its famous flagship complex connection use case. Whenever you have opening, eccentricity, something, some more complex design, this is where IDEA StatiCa shines and saves you ton of time and honestly also material. What not everybody knows is that if you apply IDEA StatiCa on standard connections, those everyday base plates, beam to beam, beam to column, splice connections, you can save equal amount of time and material as well. 75% of time, we tested it, you can save when switching from whatever solution you're having, Excel spreadsheet, some standard tools, to IDEA StatiCa, because the design itself, it's just 1/5 of the whole process. Don't forget that there is a process before and after, all the grouping, loading, sharing the data, compiling reports. The changes are always there. This is what actually where you actually waste a lot of time, and IDEA StatiCa has a way how to streamline it. Anchoring, also fascinating topic. IDEA StatiCa shines especially when you have a specific anchoring issue. You need to reinforce the concrete block. You need to know that the reinforcement actually is placed properly. This happens very often when the base plate is at the edge of the concrete block, or you need to make the concrete block of a special geometry. This is where IDEA StatiCa comes in place. Concrete discontinuities, openings, haunches, openings in beams, opening in walls, pier caps, pile caps. This is where IDEA StatiCa helps concrete engineers, and the member stability, something what global FEA doesn't give you properly. Again, this is where IDEA StatiCa shines and makes the whole calculation much simpler, much easier. Good. That will be the intro. Rose, now to you. Please share with us what's new in version 26.
Sure. Thank you so much, Jan. Let me just share my screen.
All right. Thank you, Rose. I'll be closing the camera so our audience can focus on the slides. Please go ahead.
I hope you can see my screen now.
Yes, visible.
Thanks for the yes, thank you so much for the confirmation as well. Uh, so now let's go through the highlights. There are a lot of updates, by the way, but we are going to specifically see, as Ian mentioned, the ones tailor-made for our GCC workflow. And let's get to it without any delay. So let's look at the overall update map. We have the major updates across 4 areas, which is steel, concrete, checkboard, and API. I'll walk through what has changed in each of them, the workflow that we've had before, and what or where the real update actually happened. But just as a summary, on the steel side, we have the predicted utilization, anchoring improvements for AISC, ACI codes, and some operation improvements. On the concrete side, we have the cast in plates in 3D detail, anchor cord checks as well, surface reactions, some diagnostics on the failing elements, a new addition of Ashto code, and also a new whole application of beta. Now moving to the checkboard, gets multi-material projects and direct sharing through cloud storage now. The API now exposes the stiffness, length, and full connection library, which now removes a actual bottleneck for anybody running automated workflows. Some updates are big, like cast in plates and anchor checks. Some are smaller, minor, but what I promise that they would remove the daily friction that we have with the modeling or with the analysis, etc. Now, with that note, let's start with our first update, which is the steel update. Um, the major first is the predicted utilization. So before 26.0, every parameter change, be it bolt size, plate thickness, edge distance, meant running a full CBFEM analysis again to see the actual effect on utilization. But from 26.0, for selected parametric templates, there's a ML model, which is a machine learned model that would give you a predicted utilization as soon as you change any parameter. You need not calculate the option, or like you need not hit on the calculate again. The model, which is a template that you choose, it's trained on tens of thousands of pre-calculated CBFEM runs, so that the prediction that you get represents the actual analysis behavior, but not just based on a rule of thumb. That's it. Also, the prediction is an estimate. The final verification must always be done by the engineer by running the standard EPS analysis. As of now, it is available for Euro and AISC code with EPS analysis. Moving on to the next, this is the operations usability improvement. The user in me is personally very happy with this improvement. Doesn't sound major, as I've said, but for those engineers who had to create additional weld operations just so they can only weld one part of the plate instead of the whole part, which was by default in the case of earlier versions, that's now completely sorted. And yes, I'm more happy because this is also a development request uh, from the users of GCC that we often placed. Now, coming to the details of the update, three modeling improvements here. The first is the weld settings for the stiffeners. As I've mentioned before, the web and the flange welds were kind of tied together earlier, but now you can specify them very separately. Second update would be that the circular stiffening plates, which are set as doublers. Before, you couldn't weld them directly. The usual workaround was to import the entire plate as a DXF polygon. But now the weld is defined directly, and also internally, the circular plate is divided into segments, like how we will divide it as a CHS segment, with the same segment count taken from the project setting. And the third improvement is that the total dimension of the concrete block. This again could be a minor improvement, but this would definitely create a major impact for your modeling work activities, because now in 3D scene, as you model, you can also see the total dimension of the concrete. Now let's move to the next, which is the localization. Mostly an update on the connection wizard, especially for American code users. Two changes for the users designing in AIC code. The first is that a new template based on the steel construction manual is now added to the connection wizard and would be shown on the top once you select the code as AISE. The second is that the rounding behavior for the imperial units. Before, when we were converting the values converted from metric templates would usually end up with some very eccentric decimals. But now the wizard reads the rounding from the project setting that we've already placed and applies that to uh, possibly every visible parameter. Now, again, to the next, again, a steel update, more important update for the steel to concrete anchorage workflow. Earlier, as you know, embedded plate or the anchorage often required some external checks or some external tools for the check, or some workarounds outside the normal IDEA connection workflow. But in 26.0, engineers can model cast in plates. Best part is that it can be modeled with headed studs, reinforcement, or a combination of both directly in connection application if required, which is completely aligned with the ACI 31825 provisions for the cast and connection checks. Practically, this means that now the engineer can stay inside the connection application for more of the anchorage design instead of swapping or switching the tools or moving across the tools. And if he ever requires a deeper concrete block analysis, then he can export the same to the detail, which is still available. Now, speaking about the 3D detail, now that is the next topic, and the first major update that I'd like to tell is the new sync option. The old workflow was that you export a connection model to the detail. You started doing the reinforcement work, and all of a sudden, you have a change in the connection model in the connection application. For example, the column moved, plate resized, maybe loads revised, etc. But the detail project didn't follow the same changes that you have just made in the connection application. So what you do? You'd rebuild it. But in 26.0, there is an option or a tab called Update Existing, which you'll find within the connection application. Now, once you click on that, it would sync the detail project with the latest connection data that you've just input, without you starting over again from the 3D detail. Now let's speak about what gets synced and what doesn't get synced. What gets synced is the concrete block as a whole, the cast in plate, anchors, materials, obviously the loads. What doesn't get synced would be the project settings. That is the project settings from the connection application, and the detail would remain again independent. But apart from that, all the connection detail that you have changed, as mentioned, would be definitely synced. Now that we have said about the sync option, let's see what's being transferred and modeled in 3D detail. We already mentioned about the casting plates, but now in 26.0, it is properly a full part of the 3D detail workflow. Earlier, the steel to concrete load transfer through the cast-in plates was not as direct, especially when we needed headed studs or welded reinforcement, etc. But in V26.0, cast-in plates are available as load transfer devices in 3D detail. And now engineers can combine welded reinforcement and headed studs if it is required in the project on a single plate. So the reinforcement that I just mentioned, it can be straight, it can be L-shaped, or it can also be U-shaped one. The loads can also be applied directly to the plates or through possibly a short steel stub, which would give a more realistic transfer of column forces into the plate and through the plates via the anchors and to the concrete base. Now the next question is what can we check? Mm, okay, this actually covers a workflow gap. Earlier, detail could verify the concrete block in steel to concrete connections, but anchor steel checks like tension, shear, or bending was not completely a part of the 3D detail, the 3D detail workflow. You again had to move to the connection application to do that. But V26.0 anchor steel checks are fully directly integrated into the detail. So this is useful. So the engineer doesn't have to treat the concrete block and the anchor steel as two or as separate review items. Can be just done in one whole application. Next one is again, um, yes, it's on the 3D detail module, more of a result reading improvement. Before 26.0, if we needed to understand how the support reactions was distributed over the concrete block, it was not visual, obviously. But now support reactions can be shown directly on the concrete block. Two types of views. First, we'll get to see the intensity, where we see the distribution over the supported face on like how we see in the diagram as a stress heat map. The second would be the resultant, where we get to see the magnitude and also the direction. And also the reactions can be viewed in either global or the local coordinate system. Now, the next, this is this I would say as my personal favorite from the 3D detail category, because I would say it's the most useful update for troubleshooting. Previously, if a detail analysis stopped before reaching 100% load, then what we would do, the engineer had to spend a lot of time figuring out like why exactly was the reason. Was it a capacity issue, was it a modeling issue, or was it a detailing problem? But now, when a stop criterion is reached, the software would give you the name, the reason, and the best part is that it would also highlight the location, the critical location in the 3D scene. So which means that you can start the investigation on the failure mode from the diagnosis that the application has just provided you. Next is a major update, mainly for infrastructure or bridge projects, I would say. Now, V26.0 introduces this native Astro design code. Again, the most requested update from the GCC team. Not just that, but also dedicated 2D bridge templates, normal and high strength concrete materials. You can also add ASTM reinforcement and also a few pre-stressing materials. All of these have been added to the detail module. So for engineers who are working on AIFC infrastructure or the bridge projects, the workflow is now better aligned with the design environment that you specifically are looking for. Now to the next, okay, so it's not just the Astro that's been newly introduced in 26.0, but there's a whole new section. It's a completely new application or module, which is built around the new Eurocode generation, specifically the EN 1992-2023 one. And it's called as the beta application. The current scope is reinforced concrete section for ULS checks. The best or the biggest advantage is the transparency in the results, just like how you can see in the other modules or other applications. There is a very transparent result in the background. And it's not just the summary values, but also with the detailed equations, the input values, the code references as well. Now, let's look at what's happening in the checkboard, which is the platform to connect any third-party application to IDEA StatiCa. Checkboard now supports steel and concrete entities in a single project file under one design code. So the materials, cross sections, all of them are automatically imported or mapped, so that a project with both steel connections and also the concrete walls or pedestals can now be coordinated in just one place, which is 26.0 checkboard. Not just that, you also get to select multiple members by multi-select by drag option. You can hide, isolate, or reset. You can do all the visibility controls in the new checkboard. A note to add here regarding the multi import of the materials would be that though checkboard is now the coordination layer for mixed projects, the app it opens into still have their own scope. And that brings me to the second checkboard update, which is the sharing of the projects. Now, before this, the sharing of a checkboard project could mean zipping the folder, sending large files, using any third-party applications or transfer tools to just send um, the files, or you can also use the individual viewer links. But all of this was a lot of task. But with 26.0 checkboard, the projects can now be directly shared through two ways. One is the email or via viewer URL, which makes collaboration much easier, especially when you want to send another engineer to review or to continue your work, or you need to pass the design intention to your modeling team or to your scrutinizers or even to your procurement team. You can the best part is that you can add more recipients, meaning that you can bulk share, and the receiver would get a notification in his email that a certain project has been shared to him. And these projects are stored or shared via the cloud storage and are managed through the IDEA StatiCa viewer. If you just scroll down to the My Projects in the top right menu, you will be able to find that one. From there, you can filter, search, copy, reshare the URLs, and also delete the shared files as well. The storage quota depend on the type of license that you hold. It would be different for the standard and for the enterprise, obviously bigger for the enterprise. And the best part again is that it is also available for the trial license users. So if anybody who is in here who wants to explore IDEA Statica can very well explore this part of IDEA Statica as well. The final update that I would like to speak about, which is also in a way related to our next biggest topic of today's webinar, which is the stiffness analysis. It's not entirely about the stiffness analysis, but it's just a small portion of an API update, mainly to engineers who automate parts of their work or rebuild or build repeated workflows. Now, two things exposed in the connection API in 26.0. The first is a theoretical length, which is used for the stiffness analysis. That is the M, Y, and MZ lengths. Now, that can be set or that can be edited through the API. The second one is the full desktop connection library that's now reachable from the API, which include all the set like the predefined, be it your company set or be it your locally saved private connection set. So practically, this would remove a bottleneck. That is, before you were generating connections from Grasshopper, from Python, or from structural model. You couldn't use them the same templates your team used in the desktop app. But now those templates are directly accessible, and it's more or now scriptable. Now, with that, I would like to pass the presenter to Jan just to walk us through the summary of the updates that I've just mentioned.
Thank you, Rose. Wonderful highlights. Well, it's difficult to do a summary when there is so many features that are interesting. I would probably have to go through it again and mention each and every one. I just highlighted here 3 or 4 of that we believe will have the biggest traction. And honestly, many of them were requested from the GCC region originally. So this is a call to action to everybody here on the session. Do not be afraid. Reach out to our support through the help desk. You can suggest improvements of IDEA StatiCa, and if it's a good suggestion, matches with other people suggestions, it can happen that it's developed soon by IDEA StatiCa. So as always, we would like to know which of the features that Rose just shared would make the biggest difference in your day-to-day structural design workflow. So I'm running the poll. Again, you can find it next to the chat tab on the right-hand corner. And please let us know which of the features you saw will help you the most. If you like more than just one or all of them, you have to pick. You have to pick your favorite. All right, so first votes are coming in. And I'm afraid that we pick the option that the voting is non-public. So I will have to comment. Okay, a few more seconds. All right, 5, 4, 3, 2, 1. Thank you very much. So no big surprise is the number one, utilization prediction. So obviously many people here are optimizing their connections, running iterations. Sometimes it can get endless. So really 60% of the voters here appreciate the utilization prediction in the templates that are machine learned now in IDEA StatiCa. The second silver position, project coordination through checkbot, makes sense. It's not just about the data, but the endless changes back and forth, consultant, contractors, changes on site. This really can make everybody's life much difficult, and this is actually one of the most hidden, time-consuming aspects of the project design. All right. So again, repeating, first 60% utilization prediction, second position coordination through checkbots, 25%, and the rest of the options, few votes each of them. Very good. So with this, we are switching to the second topic of today's. Rose already mentioned the stiffness analysis, now available in the API. So if you wish to automate your designs through API, Grasshopper, any advanced automation topics, you now can utilize include stiffness analysis. And this is the topic that we'll be discussing. Venki actually is preparing already. I don't think that Venki will be starting from the advanced topics such as automation, but he will be kicking it off with some basics. Right, Venki?
You're right, Jan. So I'll walk you through the stiffness analysis. Let me just share my screen.
Very good.
Okay.
Still waiting for the slides. And now it's on.
Got it. Thank you, Jan, confirming. Okay, so before we go to the stiffness analysis, most of us have assumed a connection is either pinned or rigid without verifying it. And often that works, but when it doesn't, the consequences show up as unexpected force distribution or internal stresses redistribution, unexpected ones again, and also excessive deflections or connections that doesn't behave or not in line with what the global model expects. So in this session, I'll walk you through how IDEA StatiCa can help you to verify your connection stiffness for any connection, and to check whether the assumptions made in your global analysis model have been retained in the real connection design, and what to do when it's not matching. So let me move to the main slide. So before going into how IDEA StatiCa can help, let's understand what is the connection stiffness and what are the problems which we have, which needs a solution. So the connection stiffness, in simple definition terms, it is nothing but the rotational resistance of connection components against the applied moment. So since we are talking about rotational resistance and applied moment, to calculate the stiffness, we'll be plotting a graph, which is rotation on x-axis and moment on y-axis. And depend on the calculations or analysis, we will be plotting a curve, which is moment versus rotation. And this curve is called stiffness curve. And the slope of this stiffness curve will give you the rotational stiffness. And depending on whether the stiffness curve lies in between the pinned or rigid, or stiffness curve falls above the rigid, or the curve falls below the pinned limit, there are typical classifications of these connections, which are pinned, semi-rigid, and rigid, as we already know. So moving on, let's see some of the problems associated with traditional calculations. So initially, we have to do the member analysis before we reach to the connection design, because we need inputs, the forces and sections and everything. So the first thing what comes before is the member analysis, which is global analysis model. So while designing this member analysis model, we have to assume a lot of things, like the end conditions of these structural members, which are connecting with each other, like ideal pinned condition or ideal rigid condition. I call it assumptions because we are not sure about the actual stiffness or real stiffness, because the connection itself is not done yet. So during this stage, we will be assuming the restraints or the end conditions. Once the global analysis model is analyzed, checked, everything, with all these assumptions, for strength and stability of the structure, we will push all the inputs of the global model to a connection designer. He will go through all the inputs and he will design his own connection, like providing plates, stiffening members, bolts, wells, and he will complete the connection design, and he will check for the stiffness of the real connection, what he has designed. So if the real connection stiffness is matching or in line with the global model assumptions, it's fine. If it is not, there are certain risks associated with it. Like, for example, this is just an example. If the global model has an assumption of end restraint or end condition as a rigid, while the real connection has a semi-rigid behavior, it will have incorrect moments. Like for example, the moments might be more, or the forces might be more, so on, etc. And the second example, in the global analysis model, if you assume a pinned connection, pinned restraint, you have assigned releases, and while doing the real connection design stiffness, then you got a output as partially restrained, then you are ignoring the end moments for this connection, which might be under design. So it is from this, I just want to say that the assumptions versus reality is different. So if both are not matching, there will be certain risks associated with it. So why it matters? Yeah, it's fine. Like if assumptions not matching, there are risks. So what does this risk do in a structure? Let's understand that from this slide. You can see the ULS checks, such as the internal forces or stress redistributions, even the connection force transfer of the ULS checks, which is ULS load combinations, will vary because of stiffness variation between assumption versus realistic connection stiffness. So this might end up increasing your forces or moments. Like, for example, if you design a connection with 95% utilization, if the forces have increased by maybe 6 kilonewton meter or 10 kilonewton meter, there might be a chance that your connection falls to a fail zone. It might go to above 100% utilization. And for the SLS checks, serviceability, the deflections might change, the rotations might change, and the service behavior as well changes. Initially, the code has suggested some tolerance, which is error tolerance between stiffness of assumptions between global model and connection model, like 5% for internal forces and 20% for deformations, which is okay if it is within the limits. If it is crossing these limits, then we have a problem and we have to take care of it. But it is not practical for us to check for each connection whether it falls within this percentage or not. And hence, it is always a good implication to have to verify your respective connection for its respective stiffness to ensure the connection what we are designing aligns with the global model assumptions. If it's not, we will see what to do next in the next slides. So to eliminate all these problems, you can perform the entire stiffness analysis in IDEA StatiCa with ease. Stiffness analysis is a different section in connection module itself as a separate section. And you can perform the stiffness analysis in various code like Eurocode, AISC, and so on, etc. And the output, what you get from the stiffness analysis in IDEA StatiCa are namely these three. The first one is the moment rotation curve. Since we already discussed what is moment rotation curve at the start of the session. And the next one is the stiffness value tables like initial stiffness, secant stiffness, and rotational capacity of connection, and so on, etc. And finally, the joint classification, like pin or semi-rigid or rigid. If you didn't understand like any part of this value table description or the curve itself, do not worry. We'll be talking about each of this in the next slides. So just be patient. And let's see how stiffness is actually analyzed in IDEA StatiCa. What is happening behind the closed doors. So you don't have to like do any setting option or do anything. This is just what happens behind the closed doors, like solver, how it performs the stiffness analysis to give you the output. But it's better to know like how IDEA StatiCa analyze. That's why we have this slide. So IDEA StatiCa analyzes the stiffness with the help of two internal models. First one is the full connection model. It will consider the entire members like the column, the beam, and all the connection elements like end plate, bolts, welds, so on, etc., and perform the stiffness analysis for this. And we will get a rotation of theta total. This analysis will be done by multiplying the applied loads with the help of multiplier until the resistance of this joint is reached. The resistance is reached, which is like the utilization of bolts is reached, or utilization of welds is reached, or the strain in any of these plates is reached up to 15%. So the next one, it will perform the member only stiffness, for which it will not consider any connection elements, only the members, and the rotation is calculated, and it will be named as theta1. And finally, to get the pure connection stiffness, we will be subtracting theta total minus theta1 to get a theta2 rotation. That is the rotation of this pure connection. This is how in IDEA StatiCa the stiffness is calculated. And now let's see what are the inputs which we should give or feed into IDEA StatiCa to have a proper results. And I want to highlight that these are the settings which are not optional, which are mandatory to ensure that what is there in the global model is exactly represented here, so that you will have realistic results than approximate results. You will understand why in the later slides as well. So the first input is the theoretical member length. This option will be active only if you change the analysis type from stress strain to stiffness. Once you change the analysis type to stiffness, you will have two options. One is to assign theoretical length of the member in Y plane and Z plane. So This theoretical member length is nothing but the node length of this member. So it is pretty straightforward. And at these two fields, don't leave it default. Check for the node-to-node length of this member and assign the lengths accordingly. And the second one is the minimum loading. So as explained in my previous slide, IDEA StatiCa stiffness analysis will increment your loads until the resistance is reached. So if you have assigned like you should have, you should assign some a decent magnitude of forces or moments in order for a solver to analyze the stiffness analysis properly. So IDEA StatiCa recommends that you should assign a minimum of 1 kilonewton of translational force or 1 kilonewton meter rotational force in MY, MZ, or MX. And the third one is the analyzed member. In stiffness analysis, you can analyze stiffness for only one member, and hence you have to select the member and you have to put it as set analyzed. It should be the analyzed member. Then the stiffness for only the analyzed member will be calculated and the output shows the same. And you should make sure that all these 3 points are checked before you perform your stiffness analysis. So a small demonstration of how it works. So here we have a moment connection where a beam is framing into the column, and with the end plate, bolts, and rib plates. So first step was to analyze for stress strain. This is because if it is not passing in stress strain, no point in going for stiffness. So first of all, we have to make sure that stress and strain is okay. Then you can make a copy of this. Once you make a copy, you can go to the analysis type and change the analysis type from stress strain to stiffness. And the important points to check the inputs, which is whether the member is set analyzed. Yes, it is analyzed member. Next one is the theoretical length in both planes, in Y plane and Z plane. We have to get the nodal distance, nodal length, and we have to enter those values here accordingly. And these are very important. And finally, the load cases. We have to ensure that a minimum of 1 kilonewton or 1 kilometer is inputted as loads. And finally, we can calculate. And since, as discussed, it performs 2 different internal models, so stiffness analysis will take a little more time than EPS analysis because it has to do more. Now it's done. To check the behavior of this connection, we can go to the check tab. And on the right side, you can see the 100% loads applied. In the rotational stiffness tab, you can see the tables of results along with the moment rotation graph. So here there are a lot of information, a lot of abbreviations, and a lot of values. And in the graph, there are a lot of lines, green line, yellow line, blue line, so on, etc. So it might be a bit overwhelming, but it is very simple. Let me make you understand that very clearly. To understand that very clear, let's move to the next slide, in which I prepared the details accordingly. So this is the numerical table, what we get, what we've seen in the previous demonstration, and this is the moment rotation graph, what we have seen again in the previous demonstration. So let's go through one by one to understand it very clearly. The first one is the item, which is the name of the member for which we are analyzing the stiffness analysis. In this case, it is B. If you name something else, then that name will be visible here. The stiffness analysis is performed for this member. And the component of it, like we have 3 components, rotational components, which are MX, MY, and MZ. If we are assigning the loads in any of these components, that component stiffness values only will be evaluated. If you are not inputting MZ or MX, then that will not be evaluated. Yeah, so this will be the component in which the member is loaded. it is loaded in my to check the rotation. And next one is the load case. Here the load case is named as my itself, but if we have like other names like LE1 or LE2, then the load case name will be represented accordingly here. Next one is NED, which is applied moment to calculate for the stiffness. This is an input. This is not a calculated value. So it's just input. What we have assigned in the stiffness model was coming here. And the same value, if you come to the graph, you will have a line here, the bottom line, which is MED. So if you go back, there will be the next abbreviation, which is MJRD, which stands for bending resistance of the entire connection. Like the capacity, not the okay. So MJRD is the capacity of the connection, and you can see a plot of this as well in the graph, which is here MJRD, which is just above the MED, which says the connection capacity is here, and the load the moment acting on this connection is here. So there is slight tolerance between the applied load and the failure zone. And next one is the initial stiffness, which is calculated from IDEA StatiCa stiffness analysis engine. And you can see that in the graph as well at a point here, SJNI, in the stiffness curve. So if you see the curve very closely, you can see that the curve is straight from the origin to SJNI point. Then it goes non-linear, highly. So till SJNI, the stiffness curve is linear. And after the initial stiffness, the curve remains highly non-linear. And generally, this SJINI will be at 2/3 of the capacity of the connection. Like we just calculated the capacity of the connection, which is MJRD. That value is 600.35, which is multiplied by 2/3. We'll get this line, which is 368.78. And that line coinciding with the stiffness curve will give you SJINI. And till there, it will be linear. And after that, it will be highly non-linear, and it is non-uniform of stiffness because it is not a linear curve. That's why we have a second stiffness, which is recommended by the code as well, which is the secant stiffness. That value comes after the initial stiffness. So these two are the stiffness outputs which you'll get from the stiffness analysis engine. And if you are confused about which stiffness to use, we will talk about it more in the next slides as well. And next one is the initial rotation. Initial rotation, which will be like an intersection of the stiffness curve along with the MED. You can see the line, and if you plot a line at this intersection to the x-axis, you will get the initial rotation that is tabulated here. And similarly, you have the rotation at the capacity of the connection, and L is theoretical length, which we have assigned as an input. And next one is SJR, which is fixed limit. You can see this yellow line, that is this value. And next you can see the pin limit, which is blue line here. These two are not FEM results or FEA results. These are just automatic calculations based on codal equations. And also it highly depends on theoretical length. That's why I said this input is very important. And finally, the classification, which says it is semi-rigid or rigid or so on, etc. So I told you that you have two values here, pin limit and rigid limit. How it is calculated, to understand that, let's move to the next slide. As per AIC classification, we have moment rotation graph, and we have a pin limit as 2 EI by L and rigid limit as 20 EI by L. So EI is constant and L is theoretical length, and hence if L is inaccurate, you will get the limits of pin limit as well as rigid limit not exactly as required for your respective case. That's why theoretical length is always important to get these limits accurately. And if you have to transfer the initial stiffness, it can be transferred because that is a uniform stiffness. But if you want to transfer the secant stiffness, that is non-uniform, that will be non-uniform stiffness. So to transfer that, you can do these. The graph can be exported as an image, and you can save it. You can also export it as a DXF. Which you can use it as a reference, or you can also export it as a Excel file. And this is how a picture looks like once you export it as a picture format. And you can also export it as an Excel file. And once you open Excel, all the stiffness values will be plotted against X and Y, and it will look like this. And you can form the graph even in the Excel to transfer these values into your global model if the global model accepts. Like, for example, the stat accepts only the single value for a spring constant, and other models will accept this non-uniform springs as well. So if you're working with some soft applications which accepts this nonlinear springs, then you can transfer this information directly into your global analysis model. And we have a lot of outputs from stiffness analysis to make you understand it better. Like we prepared a flowchart for you so that everything is very clear. So once you have the results, you will study the classification behavior first, whether it's a rigid or pinned or semi-rigid. If it is rigid, then you will verify in the global analysis model what is the assumption which was made. If it is also rigid, then you can leave it there. If it is pinned, then you will check in the global model again. If it is pinned again, then you will leave it there. If it is semi-rigid and it is not exactly matching with your global model, you can compare the applied moment with 2/3 of capacity of connection resistance, which we have seen the 2/3 line. So if MJED is less than 2/3 of the overall connection capacity, then you can use initial stiffness. And if it is greater, then you have to use secant stiffness. So this is how you choose between initial stiffness and secant stiffness. Once this is done, you can either transfer the stiffness values to the global model and iterate the global model to have accurate behavior as expected. And we have a few slides about common queries, what we are getting to our support. To understand it better, we made this slide, which is to understand the load path. It is important to study the load path as well in the stiffness, because as you can see, for an example, there is a beam, there is a column which is connected with the help of a haunch, and hence when moment is applied, this is deforming at the bottom and also at the top because of prying. So when moment is applied, you will have tension at the top and compression at the haunch location. So haunch is active for the load transfer path. If it deforms, then the overall connection stiffness will get reduced. So you, like, for example, not only this haunch, if you have ribs, then not exactly the plate deforms. If any of the haunch or any of the connecting plate which is active in the load transfer path is deforming, then your overall connection stiffness will reduce. Like, for example, I have a small demonstration explaining about that. Like this is a haunch connection, and we analyze it. And after analysis, we see that the classification is partially restrained, not fully restrained, but this is a moment connection, and moreover, it's a haunch connection. I want it to be a rigid connection. So I check the deformation and equivalent stresses in IDEA StatiCa, because IDEA StatiCa, you can see all the visual heat maps, and you can see certain deformations and stresses concentrated at the haunch bottom. So I will go back to the model and slightly increase the thickness of haunch I will not make any changes to the plate or bolt arrangement or weld arrangement. Now in the results, we can see that it is fully restrained. So not necessarily we have to get confused that the moment connections are rigid. We have to verify it once, and we have to check all the components in the load transfer path and ensure that nothing is deforming or nothing is not stiff. We have to ensure that everything is stiff enough to transfer the forces if that particular component is active for the load transfer. And the second query which we get is, it is safe in stress strain, it is not safe in stiffness analysis. This is a common query as well. As you see, the analysis engines or analysis models behind stress strain analysis and stiffness analysis are quite different, and hence a connection passing in stress strain analysis doesn't automatically mean that it is rigid or pinned or so on, etc. So some of the key points to highlight between the analysis are like the purpose of stress strain, it's to check strength and it's check rotational behavior, and every you have only one bearing member which receives all the forces. In stiffness analysis, all members are assumed to be supports except the analyzed member. And the loading we can load all members. Here only analyzed member can be loaded. And the capacity difference, max load before failure, and points where stiffness drops. And for the internal model itself, like super consolidated elements, it is considered as 4 times the width, and here it is 2 times the width. So do remember that if a connection is safe in strength, doesn't automatically make the stiffness as rigid or anything what we are expecting. So we have to make sure to check all this and do the stiffness analysis accordingly. And in most of the cases, if you're analyzing stiffness, the weakest deformable component in that load path contributes to the reduction in stiffness of the connection. So make sure that you check all the components which are active for the load transfer, and you read the results, which is moment rotation curve, and validate the global model to make sure that assumptions matches the realistic connections. If it's not, transfer the stiffness as a spring into your global model and recheck it again. And it is very important to read the moment rotation diagram as well to get the initial stiffness or sequence stiffness and transfer that information accordingly. And also, moment connections also need verification. I just did a haunch connection, which is a moment connection, but the classification turns out to be semi-rigid, not a rigid connection. So I have to do some alterations to make it a rigid connection. So if you have a moment connection, that doesn't make it automatically a rigid connection. And the recommended workflow: first, design your connection, run the stress strain analysis, verify every connection component. This is because if stress strain is not okay, then doing the stiffness doesn't make sense. Like, we have to go back to stress strain, iterate it again, and bring that components again to stiffness. So better first make the stress strain analysis work, then copy the item to stiffness, set analyzed, calculate, and read the classification, compare the results. If it is matching, fine. If it mismatches, either revise the connection arrangement to make it stiffer, or modify the spring stiffness in global analysis model and recheck again. And finally, document it. So that's all from me. I will pass the word back to Jan.
Thank you, Venki. So there was a comprehensive overview of stiffness analysis in IDEA StatiCa. We will almost wrap up today's session. Before we do that, as promised, for the first time ever, GSD IDEA team developed 2 applications that improve the usability and workflows with IDEA StatiCa. So let's take a look what is there for you. First application, if you struggle with generating bill of material reports or ERP data for your planning or procurement team, Bomb Extractor is very simple. Click and open app where you can upload IDEA StatiCa files, click on extract, application will give you Excel spreadsheet with 4 tabs, each tab for different type of material, plates, bolts, welds, anchors, all including the important information that your procurement team wants. Why was this application requested so much by many engineers here in the GCC? Well, not only you eliminate the potential errors when creating the BOM reports manually, copy pasting from IDEA StatiCa and other resources, obviously also from your global analysis, you have to spend the manual time. So many engineers, they spend 2 hours per average 10, 15 connection small scale project. So the bigger the project, the bigger the time saving. But this is not all. Your procurement will love you because they can get the information they need much sooner. Typically, they wait until the CAD model is done in your CAD or BIM solution, and only after that the procurement starts to procure the material they need. However, majority of the information are known much sooner after the global analysis is done and after connection design is done in IDEA StatiCa. So with BOM extractor, few clicks, and you can go and deliver the BOM reports right away. The second application, and you're actually the first ones to see that because we will be officially releasing this in the next hours, is an application called Batch Report Extractor. If you or your team is compiling the connection reports one by one, every team member handles different part of the structure. So at the end, once the connection design is done and you need to prepare a joint binder to submit it to either your consultant or to the authority, you know how tedious and time consuming that is. So with BOM extractor, once you have IDEA StatiCa files, again, you upload them, you choose the report properties, the same ones that you have available in IDEA StatiCa, and you click on generate report, and you get one report binder that you can just simply send or share with whoever stakeholder requires that. How it helps? Well, here it's obvious. You eliminate the errors in reported data, or not necessarily the errors, but the inconsistencies. Different person, different report settings. It does not match in the binder, so it needs to be redone. Whenever there is a change, you can run the analysis for all the connection and do the bulk update for the report. And of course, you have the submission-ready report ready at your fingertips, just a few clicks away. So I will be doing 3 things now. I will be sharing one poll. Feel free to vote which of those 2 applications are interesting for you and it would improve your workflow. You can choose from both of them, one of them or none. And next to it, I'm sharing in the handout section, there are 2 links for both BOM extractor and bulk report extractor. If you just download and open the link, it'll get you to the dedicated web page on GSD IDEA web, and you can learn more, see the FAQs, watch the video, and learn more about how our 2 applications work. And with that, we're almost wrapping the section. The last 2 topics, just reminders. First, for all GSD IDEA customers, we're doing regular sessions. Valuable whether you're new or already a seasoned structural engineer, seasoned users of IDEA StatiCa. This month, there are 3 planned. One already happened last week. That one was for concrete. This week, tomorrow, learn how you can save up to 75% on your time on standard connection, on those regular connections that you do with standard Excel spreadsheet or typically RAM connections, Limcon, sometimes Procon, and these simplified tools. So Rose will show you tomorrow how this can be done much faster. The week after, May 21st, there's the advanced topics on steel, how to do complex connections, explanation on the analysis, etc., etc. The week after, we have a free week, as there will be Eid holidays. Last reminder, join IDEA StatiCa Wolf user group. It's a closed group for only GCC members. So if you're doing projects on GCC, join the group. You will not miss any update. We post there regularly about webinars, about IDEA StatiCa, tips and tricks, updates, all the interesting stories. So you make sure that it's not lost in your feed. And with that, we're wrapping our session. If there is any question you have, please put it to the chat. We will be staying and answering those questions. That's it for today. Thank you very much for being with us, and see you at the next webinar. Take care. Bye-bye.